Hello, y'all, and welcome to Lesson 37, Structure 2.1.3. This is part two. This is where we're going to talk about ionic compounds. Specifically, now we're going to explain the physical properties of ionic compounds in more detail as we touched on them in the last lesson. So, when we think of ionic compounds, generally what scientists tend to think of are things such as like salts, maybe ceramics, or maybe minerals. And minerals. And it's often good to start thinking about things you know when you want to define their properties. So salts are generally pretty easy to think about: calcium chloride, sodium chloride, magnesium chloride, aluminum fluoride. Generally, we think of these binary compounds that are metal and non-metal as a salt. And generally, the most common one is table salt, sodium chloride. And so it's often helpful to think about sodium chloride as a main salt, which also is one of the things that demonstrates the properties of these compounds very, very well. So we're going to look at sodium chloride as we talk about the many properties of compounds. So starting with property one, let's look at melting points. Now, in the ionic compounds I listed above here, salt, ceramics, minerals, those generally are often solid at room temperature. Now, water is a liquid at room temperature, and water has what we'd consider a low melting point. Therefore, if it's solid at room temperature, it needs a lot of heat to melt. Needs lots of heat to melt. So we'll think about our good old friend salt. When you think about salt, try and think about a time you've seen salt in the liquid phase, not dissolved, so not mixed in water, because we can always put in water and it separates and dissolves in that solution, but actually liquid salt. And the most of you probably would say you've never seen that because it takes a lot of heat. So we generally say that these have high melting points. So that's a general trend for almost all ionic compounds. They tend to have a very, very high melting point. And just to be clear, we went over this earlier. Melting point is the temp where a substance goes from solid to liquid. And generally, it can be at different pressures and different temperatures when we have different pressures, but at room temperature and sorry, at room pressure, atmospheric pressure, 1 atmosphere, 100 kilopascals is generally what we tend to do this at. So ionic compounds tend to have a very high melting point. So that's the first property. Next, we can look at volatility. We've discussed volatility before, but this is the tendency for a substance to sublime or go from, whoops, not gas, uh, solid to gas, or even liquid to gas. So sublime isn't actually the right word. We're gonna delete that. To become a gas. So while we look at a lot of things, a lot of ionic compounds are solid, and we don't often see them becoming gases. But a good example of something that has high volatility would be like a perfume. And you know it has high volatility because you smell it. Perfumes. Because they turn into a gas and you smell that. You can smell the gas particles. Smell gas particles. Now think of any rocks or salt and think about a time you could smell that. The truth is you can't. They don't really smell anything. That's because they don't readily convert to gas. Ionic compounds don't readily become gases. So we would say that is a very low volatility. Now, there's a couple exceptions. If you've heard of things like smelling salts, whoops, don't want my highlighter, just want a different color. To wake someone up, you might see them in medical shows or something. And smelling salts are a high volatility solid. Other things like things solids that give off smells often we consider to be high volatility because you can smell them. And while salts may not have a smell that you can smell, they don't often become a gas. So we do have a couple exceptions, but on average, they have a very low volatility. Now, the other key aspect here is this is actually related to lattice enthalpy because lattice enthalpy is the energy enthalpy is it's the energy to go from a solid lattice to a gaseous ion. Gaseous ion. So generally, high lattice enthalpy would equate to low volatility is equal to low volatility, meaning it takes volatility every time. It takes a lot of energy to rip a ion off that lattice and become a gas. So that is property number two. Property number three, solubility. Ility. All the ilities. Too many I's, too many L's, too many T's. So solubility, straightforward, is the ease of a solid to dissolve in water. That's generally what we think of it, but generally in a solvent. But more specifically, not just dissolve in water and become an aqueous solution. Aqueous solution. So when you think about something like salt, generally you know that salt dissolves in water. You put it in, you mix it, and the salt disappears, but the water tastes salty. And that's because ionic compounds have high solubility. Ionic compounds break into individual ions as they dissolve due to high solubility. So they just like to break apart. And we can see this when we take salt and put it in water. So we're going to do a little diagram here. Just bear with me a moment as you witness my terrible art skills. And we have these cups of water, and we'll do a little before, after, and we have our particles together. Now, what I'm going to do is I'm just going to put a little network of positives and negatives so that you know this is an ionic compound. And there we go. So when we put this salt in water, and we'll say this is just regular NaCl, it actually becomes something new. And by something new, honestly, I mean the exact same thing. The only difference is these particles separate and they become their own individual free-floating ions. We can even have a couple next to each other that share a charge because they're not actually next to each other. They're overall distributed throughout the system. And we actually even write it differently. So this is NaCl solid, and now it becomes NaCl aqueous. And this is what it means for a ionic compound to be aqueous. It's for its particles to separate into separate ions. Even further, we can actually write a different equation. NaCl solid more realistically becomes Na plus ions aqueous plus Cl minus ions aqueous. And for this to happen, we are actually breaking the lattice. So we are breaking through that lattice enthalpy, which water has the ability to do, and it's why it's such a good solvent. It's so good at taking ionic compounds and breaking them into their constituent parts. So generally, we say that ionic compounds are mostly soluble. There are many that aren't, but more often than not, whoops, soluble. There are many that are not soluble, but most of them will be, and most will dissolve in water. It depends on two things. Depends on, number one, the lattice enthalpy. A low lattice enthalpy would be more soluble. So lattice enthalpy is specifically a measure of the strength of ionic bonds. It also depends on the strength of the bonds water forms with the ions. So water is actually going to form bonds with these individual ions. We're going to talk about this in much greater detail later in a few lessons way down the road when we're talking about enthalpy of hydration. But basically, what you end up getting is little water molecules that surround each individual ion. With the positive ions, you get the oxygen of the water attached, and with the negative ions, you get the hydrogen attached. And so you make these little structures within each ion. So this is just kind of a magnified view of what actually happens here. So we can go ahead and try and make this a little clearer. Do one of these like pop outs. So this is kind of what's happening to dissolve a solid. So this is going to have some attractive force, and that is the strength of those bonds. So that's what solubility depends on. Um, a couple key factors that you need to know about soluble mixtures is that soluble compounds form homogeneous mixtures or homogeneous solutions. That's really important for when we're doing solutions chemistry and we're mixing two different solutions and we had dissolved something. We want to know that that solution is homogeneous and it is even throughout. So we can take a tablespoon off the top or a tablespoon off the bottom and have the same solution. Furthermore, we have the other term insoluble. If you've never heard that one before, but it basically means does not dissolve. And something we'll also learn quite a bit later is that solubility is more of a spectrum. Some things dissolve only up to a certain point, and that point changes for each compound, for the temperature, etc. So for now, that's solubility. All right, we're going to move on to one of the final ones, not the final, second to last. So this is conductivity. And specifically, we're talking about electrical conductivity here, electrical conductivity. And what do we actually mean by electrical conductivity? Because we need that definition first. And generally, this is considered as the ability for charged particles to move across a region. Now, generally, when we think about electrical conductivity in like wires, so if we have like, for example, a wire, we think of it as electrons moving through. Now, electrons are charged particles, and that is electrically conductive, but we have other charged particles in substances. For example, in our salt water, we have positive and negative cations and anions, respectively. And those moving also carry a charge that would be electrically conductive. So with ionic compounds, it's a little different for each situation. A solid ionic compound, well, solid ionic compounds have their particles very rigid and fixed. So they have rigid and fixed ions in a crystal lattice structure, meaning they can't move at all. So this is very much not conductive. And that makes a bit of sense. If you just look at a salt crystal or rock, most rocks are ionic compounds or maybe a ceramic pot. You don't think of that as something that can conduct an electrical charge. You don't worry about putting a battery on the ground, or even when you are putting a grounding rod in a home, it goes through the rock into the ground. You're not worried about that. So solid ionic compounds are non-conductive. But what if we melt it? What if we look at molten ionic ionic compounds? Well, molten ionic compounds are in the liquid state. That's what it means for it to be molten. Now, when they're in the liquid state, the lattice is broken. We've put enough energy in there to break it, and it takes a lot of energy. These are hot, molten liquid ions. And because the lattice is broken, the ions can move. And you kind of know this already, because when we look at particle theory, if you have if you have your solid, it's a fixed structure. I don't really know what I'm drawing here. That's a solid. But in a liquid, we need a container because they kind of slide around each other and they just move. And so these particles can move around. Should have done those arrows in a different color, but it doesn't matter. Now, because the ions can move around, this is conductive because it follows the definition. We have the ability for charged particles to move across a region. The particles can move through that region. All right, the last situation we generally think about is aqueous ionic compounds. Just going to keep a little consistency here. Now, once again, the ions are free to move around. We see that appear in our image. We have our ions just kind of moving around this solution. They don't really care. They're bonded to their water and they're happy. So because those ions are free to move around, this is also, let's keep it consistent, conductive. This is why salt water is conductive. You may have heard before that if you take a solution of water, just regular water, this is not conductive. Pure water does not conduct electricity, but as soon as you put those ions in it, you have your little pluses all around. You got your little minuses around. Now, the salt water is very conductive. It can allow for the movement of those particles because they are free to go with the current. The positive can go to the negative, negative can go to positive, etc. So this is the conductivity of solids, moltens, and aqueous ionic compounds. So we're on to the last one, brittleness. If you've ever looked at salt, it's in these crystals or rocks. They break, they can form crystals. But the thing is, ionic compounds are very brittle. Missed an R there. Very brittle. Ionic compounds break easily. And they're pretty strong, but once they break, they really break. They just go. And that actually has to do with their lattice structure. So if we look at an ionic compound, and I'm going to have to draw a little bit. So you know what? I'm going to pause the video and come back. Give me just a moment. And I'm back. So I have a little lattice here of positives and negatives. And the reds will be positives and the blue will be negative. And you can see this lattice is very strongly held. So this is our ionic lattice. Now, imagine you were to apply blunt impact to this side, just straight down to this entire region, and you apply that force. Well, something's going to happen here. So let's copy this and we'll paste it. And so that whole region will shift. So impact. And now you notice something a little weird. You might notice that we have a positive next to a positive, a negative next to a negative, positive, positive, negative, negative, positive, positive, negative, negative. And the problem is these will create a repulsive force. These will repel, which will cause that whole plane to just break apart. And this is what we consider to be that impact or that fracture. So this might move away and it fractures. And so that's what we call brittleness. That's why it snaps so easily. Shifted the layer, once we shift that shift layer, it gets pushed apart by electrostatic forces, pushed by electric force. So this kind of explains all those little weird things that happen with our compounds. And once again, I think it's very helpful to think about an ionic compound and think of salt. Salt breaks really easily. You can crush it up, and that shows its brittleness. Well, if you try and crush up some metal, you might just flatten it. Um, it dissolves in water, so it's so it's soluble. It is conductive in water, but it's not conductive as a solid. Furthermore, it doesn't become a gas because you don't smell that salt like you do when you smell salt water, which has been carried by droplets of water. But without the water to carry it, you don't smell it. And it doesn't melt, so we think of it as a high melting point. So as you go through the properties of ionic compounds or the properties of any compound whatsoever, it's very helpful to think of an example that you know, such as table salt. Anyways, I hope this helps and have a great day.